So again, we're entering now chapter 6. Today's day 1 of chapter 6. You are going to, in your groups, be starting out with that chapter 2, day 2. That was the video we watched way back when. When I asked you to collect 20 data points that you randomly selected from that spreadsheet of data that I sent you. And again, I've said just have that data set out because you'll be looking at that. But get your 20 data points. If you collected the other 40, so you have your full set of 60, then you're probably going to be winning today. I told you we'd be coming back to this really soon, and we're now here. And I said if you didn't do it, go back and do it now. So if you still haven't done it, then you're way behind. We don't have time for you to randomly collect your data today. If you made up data, don't use it because you will not discover the investigative properties we're trying to get to today. If all of the people in your group made up data or didn't do it, you're kind of screwed because you're not going to get much out of what we're going to start with. But what you're going to do is I want you to go to your windows, start with creating a histogram of your 60 data points. Draw that on there, histogram of your 60 data points. If multiple people have different ones, just pick one of your sets of 60. But plot one of those 60 sets, and then I want you to describe that graph. Shape, center, spread, outliers. That might mean that you have to take that data, put it into the stat.blue, find the average, find the standard deviation, those kind of things. All right, so we just did this, and you graphed your data, and as we said, they ended up being right skewed. So again, when discussing shape, center, spread, and outliers, a simple statement of saying, looking at this graph, it appears to be right skewed. And then what corroborates that is when we talk about the mean and the median, the centers. And since the mean is greater than the median, that fits with the fact that my data was right skewed. And then if you do say it appears that there might be one average out there that might be an outlier, you would then need to show the calculations for that. All right, so everything we do and communicate mathematically in words, we need to have calculation corroborating that. All right. And most of what we're going to do for calculations, we'll be using technology. I'm not going to ask you to do much of that by hand, or if any of it by hand. We did the IQR. We've already done that by hand. So we'll find ways to work past that. But that's also like a entry-level calculation. We're going to do some more sophisticated calculations soon. And in that, we'll be doing other ways to determine if something is an outlier. So then I pulled up the whole data set again, and I took that and I found, but what I want you to be able to do is when you're thinking about the summary statistics of this original data, which I just showed you, how does that compare to the plot of the averages that you just did? Now, if you were in a group that didn't have your full set of 60 data points, I would encourage you to go and do that on your own now. Find those 60 data points that are all averages from samples of size 3, make a plot, and then summary statistics, and here's what it looked like. So that was the raw data. How does that look compared to what data you had? You're thinking about that. How is it similar? How is it different? All right, you're thinking, how is my data, the graphs that you just did, how is it similar or different to this? How were these values similar or different to what you had? All right, so again, this was from the raw data. And if you don't have that raw data set yet, shoot me an email and I'll email it to you. The document that I tried to share a long time ago got messed up because I had to give everybody access and write privileges. And then a few people got in there and they're manipulating data, and then it all got just out of whack. So I'll email you directly an Excel file with this data in it. So if you don't have it, let me know in an email. I'll reply with it as an attachment. But when you're looking at that, first off, I look at this and say, oh, well, they're both right skewed. But there was one very clear difference that I saw in many of them, and that is there were not many. There obviously not as many data points if you did counts. All right. And this, what was the maximum bin that anybody had? Anybody remember what their largest average was of the three? Of your raw data? What the largest 3 average was? Like 6, I think I saw someone that had like a 619 as an average for 3 data points. Did anybody have anything else similar to that? Or in that range. You might be looking at your, but anyways, this one goes all the way out here because there was like someone who had like 900 some. We don't see a lot of these that are there just because they're so short. But that looks like there's one in that range. There's one, looks like there's almost like one in each of those ranges. And then there's a couple here. So one of the differences you would notice is that the range of values for the raw data goes from 0 to 900 something. All right. The range of values that you had when you did your calculations was less than that. What were the standard deviations most of you had? About 100? Okay. This is called foreshadowing. Someone got their calculator on them? What is 147.5 divided by the square root of 3? How much? 85.1, okay. So this is what the average of samples of size 3 would be, or should have been. So while ours were all about 100, if we did all of them, we would actually get it to be about 85.1. We'll talk about this later, and it'll make sense why that number is 3. All right. How it would compare to what we had here. And be ready to have a discussion on that in a future class. All right. This is the second part that we're not going to hit on today, but I want you to start thinking about and be ready to start having conversation about. So again, this is being videoed, so you can do that. Other people are like instinctively snap photos if you want. But why do you think these averages are close? The averages, the X bars, why were the averages close from what you did in your distribution compared to the raw data distribution? But the standard deviations are different. Why are the shapes different or same? I should have said, are the shapes different? Shouldn't have had the word why there. Are the shapes different? Yes or no, and why? Why do you think they're different? What would happen if we took samples of size 5 or 10 or 20? And this is what we're actually going to do in our next session together, is look at what are called sampling distributions. But before we go too far into that, let's just jump back and talk about what's going on here in chapter 6 that we started to talk about in chapter 5 at the end. And this is the idea of a standardized score. And I think I gave you the z-score formula. I'll write it down again. Not x bar, we'll call it x minus mu over sigma. And if we don't have mu and sigma, we will approximate it with x minus x bar over s. All right, so if you have a sample, we'll use a standardized score relative to the sample. If we have a whole population, we'll use mu and sigma. But these were the cell phone contacts that we collected data from at the beginning of class. And the first thing that we're going to say is find the standardized score of the person who has 100 cell phone contacts. Ooh, stop moving that around. There we go. All right, so standardized score of the person who had 100 cell phones. The moment you see these words, standardized score, you need to be instinctively thinking z-score. All right, and eventually it'll be a t-score, and then later on it'll be a chi-squared value or an f value. And they'll all pretty much have the same idea and concept behind how we do it, but we got to start somewhere, so we're starting with this one. So x minus mu over sigma, or x minus x bar over s. X is always the data value that we have that we're wondering about. So in this case, my x is 100. My x bar is down here. That's my mean. So that's 187.4. And some of you are probably realizing at this point I should probably have my calculator out because we're going to calculate this, and I should just verify that I'm getting the right number, that you're using our calculators the right way. And then S is the standard deviation, which is right here. So when we're doing our standardized score, I'm going to write Z equals 100 minus, actually let me just do this first. I'm going to write the formula, and then I'm going to put numbers in. The reason why I write the formula first, and you should be in the habit of writing the formula first, is if you miswrite something down but then carry it out the right way, I'll look and say, oh, they grabbed the wrong nugget of information, but they did all their calculations the right way. You have the right understanding. At least you're still in that ballpark for a 3 on an exam test, or a question on the exam. So like they're mostly there. It's a substantive response. And then I plug in numbers, 100 minus 187.4 divided by S, which was 147.518. And I find that z-score is, this is my pause where someone then shouts out the answer. Negative 0.59. Does it make sense that it's negative? My cell phone numbers was 100. My average was 187. I'm below average, which means my z-score is negative. So that makes sense. 0.59 means I am 0.59 standard deviations below the mean. So if I have a z-score of this, I know that whatever the score was, I know what it is right here, but if I had only been given the z-score, I would know that the value that I'm wondering about is 0.59 standard deviations below the mean. That's what the negative mean. So we're saying, what does this number tell us? That's what it tells us. It tells its relative position with respect to where the mean is, as well as with respect to what the standard deviation is. Can I use the empirical rule with this data set? Shake your heads and say, no. Empirical rule, we said, only works with normal curves. This is clearly right skewed. All right, moving on. So the standardization formula, I've said it once, I've said it again, and if you're remembering this sheet from the exam, it's on there, but it's in words. And the words are, well, what do they say? They call it the standardized test statistic. And it will be statistic minus parameter divided by standard deviation of the statistic. Standard deviation of the statistic. Why so many words? Because we're going to use this for a lot of different tests we're going to run. With like I've already mentioned it, the z-test, the t-test, the chi-squared test, the f-test, an ANOVA test. They all have different tests, but how they go about it is basically the same way. So for right now, we're with z. It'll be my statistic, which is x, the data point that I'm coming from, minus the parameter. And the parameter I'm wondering about is the mean. I'm going to compare a data value to the mean. I could actually do something with the standard deviation, but again, that's going to be outside of the scope of this class. And then standard deviation of the statistic is sigma. So that's why I said, here's the equation, but this is the more generalized view of it. This is how we're starting out to use it. And z is the standard normal value. And we'll talk about a z-curve here in a second. So a z-curve is a standard normal curve. We got normal curves and we got the standard normal curve. Here is a standard normal curve because it says standard normal curve. Across the bottom, these are z-scores, 0, 1, 2, and 3. To the left, -1, -2, -3. This is overlaid with SAT scores because it's related to another problem we're going to look at later. But if the mean was 1150, that means the mean of a z-score is 0. Why? Z equals x minus mu over sigma. If my x value is 1150, I would go 1150 minus the average, and the average was 1150. So I'm going to have 0 over sigma, so the mean is also a z-score of 0. A standard normal curve is symmetric. We talked empirical rule between one standard deviation above and below is about 68% of the data. If I go 2 above and 2 below, that area inside is about 95. Between 3 above and 3 below is almost all of it, 99.7. And that's just a generalized idea. When we're talking specifics, we're actually going to look and say, well, what's the likelihood that I'm above a certain value? So we're going to start by learning how to use this table and this. And at the end of class, there'll be a little bit of time left I'll keep so that if you have a graphing calculator, you can stick around and I'll show you how to use that super fast. If you don't have to stay. We're also going to use a computer applet here in a moment, so we'll all have access to this method for doing calculations. But here's what it says. So if I do this, I find a z-score, and I go, oh, my z-score is 1.53, and I want to find this area up here. If you're in calculus, you could take the antiderivative of the equation, which is it's a beast of an equation, but you could do it and find the area from 1.53 to positive infinity. Lucky for us, we don't have to have calculus for this class. So instead, we're given these tables. So this is part of Appendix H in our textbook, which I'll show you how to get to there in a second. But it's in Appendix H, and you can look at this table. And if I look at this table, there was the 1.5, and my number was 1.53. So I'm going to go across to the column that says 03. Are we all tracking here? Here's 03. That's the column. Here's the 1.5. That's the row. And it gives me a value of 0.0630. What does that mean? I have to look at the original picture to know what that means. This table gives me that tail area. So I go back to this problem. But that's not the tail area that I'm asked for. The table gives me this tail area. I want this tail area. Well, this is the joy of the normal curve. It's symmetric. So if the tail area would be down here, this tail area up there would be the same. 0.06, I forget, 83 I think is what I said it was. 1.53. 0.0630. I was off by a little bit. I read my table, okay? 0630. What does that mean? That means that the probability that z is greater than 1.53 is equal to 0.0630, or about 6.3%. If this were an actual SAT question, we'd be looking and say, hey, if you were this particular score, what's the probability that someone scored at or above you? And the answer would be 6.3%. We could also do this and say, what's your percentile rank? Rank is from the bottom up to your position. Well, if this is 0.63, I could do 1 minus that, and that would tell me your percentile rank. So here we go. The height of a 15 to 18-year-old males from Chile from 2009. I apologize that all my data sets are old. I'm old. They were new at one point in my teaching career. But from 2009 to 2010 was 170 with a standard deviation of 6.28. Males are known to follow a normal distribution for their heights. Good information to know. The minute they say that, anytime I'm doing a problem, that's a terrible horizontal line, I'm going to draw a picture, and I'm going to have a normal curve. I'm going to center it at whatever they tell me the center is, 170. And then they tell me 3 standard deviations above, and then 3 standard deviations below. 6.28, I'm just going to put in one value there. That's supposed to be an arrow. So that'd be 176.28. Because that's 1 standard deviation above 170. Question says, what's the probability the person selected at random from this population is over 168 centimeters tall? I need to draw my line in, so 168 is going to be about there. Do these have to be exact? No, but they should be close. I'm only 2 centimeters below, so I'm not even a full standard deviation below. I would do that, and then it says what's probably, I would be at, person will be over. Going to shade like this. The process would be, after I've done this, after I've drawn my picture, shown that I understand it said normal curve, I label it appropriately with the mean and my location, my critical value, my 168. That's the point of interest that I'm looking at. I'm going to then do a z-score. 168 minus mu, 170, divided by the standard deviation, 6.28. And everybody in the classroom that has a calculator is finding that for me quickly. Making sure to put parentheses in the right place so you're not just dividing the 170 by 6.28. And I'll get a z-score of negative 0.81. Negative 0.32. All right. So then I take that negative 0.32, I go over here to my table, which I'm going to blow up so we can look at it. And I'm going to look for 0.3, which is right there, over to the O2 row, because this is the O2 column. On the O3, so O32 is 3745. Again, that's the area of the tail. And I said that was, let's see, 3745, which means this area right here is 0.3745. That would be this area. Is that my area of interest? No. So in order to use the table, I found that tail area, but that's not the area I wanted. I want the other area. This is remembering that the area under the entire curve is 1, so I take 1 minus that and find that this area up here is 0.6255, or 1 minus 0.3745. Now, if I did my subtraction in my head correctly, that's the right number. If you just checked my work and that's not the right number, you'll tell me, I hope. But that would be then the area. So notation-wise, that would have been, over here on the left, I'll do it in green, the probability that x is over 168 is equal to 0.6255. Or there's a 62.55% chance that a person selected at random from this population will have a height over 168 centimeters. Do we actually have to say all that? Yeah. You should get in the habit of saying all of that. Words are very important. What's the likelihood they're shorter than 159? Probability that x is less than 159. I do the same process. Z equals 159 minus 170 divided by 168. Well, what's my 6.28? It's to the left of the mean, so again, I know it's going to be negative. And someone's going to shout out that answer for me. It's negative 1.75. Go to my table. The 1.7 row, the O5 column, it's right here, 0.0401. 0401. So if this were the z curve, I label it with z. The 0 is my center. Negative 1.75 was my z-score. The table gives me the area to the left. All right, the table to the left is that area there. And the question asks for being less than 159. So in this way, the table is giving me the value I do want. So it's going to be a direct solve. So that would be 0.0401. Or there is approximately a 4.01% chance that a person selected at random will be shorter than 159 centimeters. And then the last one down there, the third part of this problem is between 170. I want to be between 159 and 163. This area. Need to find the z-score for both. Well, we already know this one. The z-score for that is negative 1.75. And we know that this area down here that we don't want is 0.0401. Find the z-score for 163. Look at the table and find that number. So then that's the website that we're going to be using. So when we've done it, if you just lop off applets right after that and just like bloop, get rid of that, this will give you the list of all the different types and many more that we're gonna use. So Bogner here came up with way more than what we're going to use for the scope of this class. But they're all right there. You just got to figure out which one to use. There's the example that we just did in class. Except I think I have 168 there. We did 163. All right, so now we're going to do this in reverse order. Suppose x has a normal curve. So I'm going to draw a normal curve. Centered at 8. I'm going to mark 3 ticks to the right and to the left. This is x. So my standard deviation is 9, which means this is negative 1 and this is 17. What value will have a standard deviation score of 0.67? So a z-score of 0.67 will be right about there. How do I know? Well, it's positive 0.67, so it's to the right of the mean. It's not above 1, so it's less than 1 standard deviation. And 1 standard deviation is there, that's 17. So here's what I have. I'm going to remember my formula. Z equals x minus mu over sigma. 0.67 equals x minus 8 divided by 9. And now it's algebra. Multiply both sides by 9, add the 8, and that will tell you what your x score is for that value. Pretty straightforward on this. A little bit more work if I have to find, I don't want to do that one. Oh, this one. I want to do this one. 70% of the time. It takes more than how many minutes to find a parking space? The mean is 5, it says. Standard deviation is 2. 1, 2, 3, or 2, 4, 6. That's 11. 2, 4, 6. That's negative 1, so that doesn't make sense for time, but we'll just go with it. 70% of the time, it takes more than how many minutes? So somewhere over here on the left is a value, and to the right of it is 70%. If we go back to that applet and in the red area, type the value 0.7. So getting there, this area was, sorry, we plugged it in and it gave me a number of 3.95 and something. All right, this all becomes a matter of, am I using the right tech tool to get here? So back in the day, you actually had to way back, we calculated this manually. I was right on the tail end of that through college. Not fun. Then after that, it's reading a bunch of mathematical tables. And up until the last couple years, that's pretty much how all the stats students have had to do it, by reading tables, which is why I showed you the table. And then we're not going to worry about that. But if you have a graphing calculator, our textbook actually has very clear directions about how to type it into your graphing calculator using stuff called the normal CDF, lower bound, upper bound, whatever the mean value is and the standard deviation is, and it would just give you exactly those direct statistics when we're calculating them out. So there we go. That brings us to the conclusion of today. I'll see you next time when we'll finish up info on the normal curve.